Right, so question 7. What are you likely to do after finding a shear force diagram? You're likely to be asked to sketch the bending moment diagram. So once you've got to this stage, hopefully you'll be ready to be able to draw a bending moment diagram. So please pause the video and see if you can sketch what the bending moment diagram is going to be. And then I'll show you how I would tackle this. There's two ways to do this, and you might have to read carefully what the instructions are, because the instructions in the exam might be asking you to do accurate equations, or it might just want a rough sketch. So if it wants a rough sketch, one approach you could do is to actually use your shape of your shear force diagram and then plot it based upon that. So we know that the maximum is 1400 and it's going to be a negative. Okay, so this area here, when I found that to be minus 1400. And I know that it should drop down to 0 at the end. This area here, what's that? That's another square. Okay. So it's got a width of 1. And it's got 200 there. So you could find it based, find what we're going to be here. So we'll be minus 200 at this point. So we start at 0. So we've got m over kilonewton meters. Here we've got x divided by m there. And the next bit is kind of like a house sort of shape in it. So you could work out that area. You could split this into a triangle and a square. And you'll find that when you work out that area, you should get a drop of 1200. Be able to interpret the graph here, since this is telling me how my curve should be going. So this tells me that it's increasing, so it's becoming more curvy, if you like. And this is slightly lower. If this was at the top there, if it was 0, then it would be saying that it's actually flat. So we've got a bit of a bend, and it should be bending a bit more when we get down there. So it's going to look something like that. So that could be a very rough sketch, so we're just approximating the areas that we're finding. We're interpreting what the shape should look like, and that could be one way of doing a sketch. Another way of doing the sketch, of course, is doing it sort of algebraically, and you could then be looking at how your m equation should be varying. So between a and b, you can then say that m, and we've got this arbitrary position x here between that, and we look left of us. So we see left of us there's this 200, and we imagine we've got a pivot, and we're going to sum up moments left of us around going in a clockwise sense. So that is coming downwards, so minus 200. And what's this distance? It's x. And so we would want to plot something which follows the rule minus 200 times x for this particular section. Then for the next section, from B to C, we then imagine that we are going to do the same thing. So we look left of us, and what can we see causing moments? Well, we've still got the first one, causing moment. And here you can either memorize the formula or kind of work it out in your head. What it's saying is from this distance to this distance would be the amount of UDL that I've got. So my UDL is trying to go downward, so we'll put the UDL value to 50. So I've got this amount of UDL. So we're now at position X. The starting point for my UDL is at 1 meter. So I've got X, take away 1 amount of UDL force. And where is this section acting? It's acting in the middle. Okay. So if it's acting in the middle, then what is this distance from here to here? Well, this distance from here to the beginning of the UDL is X take away 1. So this distance from here to halfway to the center of this section of the UDL is half X take away 1. Okay, so that's one way to work it out. I think it's not in your formula booklet, but the other way it would be to use to memorize the formula, sort of the cheat way, which was just saying that if you're moving through a UDL, use the formula UDL value, divide it by a half, X, take away the start position of the UDL, all squared. So you could use that cheat formula to come up with the same thing. So let's tidy this up a little bit before we move on. Minus 200 times X minus 25 times X take away 1 squared. Now we want to work out what the M function should be when we could make a note of the position of X here. So this is between 0 and 1. This is between 1 and 5. And then C to D, I want my M function to be whatever turning moments I can see left of me. Well, the first one doesn't change, so minus 200x. Now the UDL is completely left of us, so the effect of its turning moment will be just what the whole total UDL is pushing downwards. So the whole total UDL has a total of 200 kilonewtons, and once you've kind of moved through the UDL, it will then be effectively acting in the middle. So where is its middle? It will be between 5 and 1. So 5 and 1, where's the middle of that? 1 plus 5 divided by 2 gives me 3. So the middle will be acting at position X equals 3. So we've got minus 200. This is distance X. It's now acting at position 3 when we've gone past it. So it's X take away 3. Okay, so you've got to remember that once you've gone past the UDL, you then need to treat your UDL as if it's a concentrated load acting in the middle of the UDL. What's the distance from X to this position? well, that occurs at 5. Now this reaction force is going upwards, so plus, and it is a distance x take away 5 from my moving pivot. And I don't really need to take it all the way to the end. This is enough. So these are my 1, 2, 3 plots that I need to do. You could put them in your calculator and create some data points. You only need 2 data points for this function and this function. So this is from 5 to 10. But for this one here, you probably want to use the table function on your calculator to be able to plot some points. So that's if you're doing it using a more of an algebraic approach, and then you maybe would want to create a table of what m is for certain x values. So the logical one here would be to find out what m equals when x equals 1, when x equals 0, so you can see that's 0, when x equals 1, and then probably maybe I would say steps of 1 or steps of a half, so 2, 3, 4, and 5. So when we're at this position, and then when we're at this position, it's a straight line, so we just need another value there at 10. Okay, so you will use these calculations here. So we've got an A to B here. We've got the B to C values here, and the C to D values going in there. So that's fill in those tables, plot them up, and that's the other way to do it. So this is the MD solids solution. As you can see, it's quite a slight curve. This triangle bit is not particularly pronounced. Straight line, minus 200, minus 1400. And yeah, so that's my bending moment diagram. Okay, right, onwards and upwards, I guess.